Well, we're continuing on with our discussion of nuclear chemistry. We've talked about natural radioactivity, and now we're talking about induced reactions. And so today we're going to talk about section 215, synthetic elements. So go ahead and actually take a few seconds to copy down these notes. Okay, so we're going to start with the talking about the transuranium elements, because anything above 92, so these elements are with atomic numbers greater than 92. Anything above 92 is not a natural element. These were produced by nuclear bombardment. And Ernest Rutherford used nuclear bombardment to cause the first known induced transmutation in 1919. So this technology is only about 100 years old. We've only been doing this for about 100 years. And he bombarded a nitrogen atom with an alpha particle and produced oxygen 17 and hydrogen. Now we're able to produce elements up to 118 through nuclear bombardment that we have discovered, and that is by bombarding uranium. And also, and actually above 92, these were not produced until 1940. And that was about the time that they were doing research on atomic bomb. And then more elements were discovered when they were doing experiments with the hydrogen bomb, with fusion. So there's more history of that in your book, but you can take a look at that if you're interested in that. What I want to talk about more is mass defect in nuclear binding energy. This is information that you'll need to know to work on your lab next week as well. So take a few seconds to copy this down. Okay, so one thing we need to know, and this is a really curious thing, is that the mass of the nucleus is less than the sum of its components. And you're going to say, now, wait a minute. We know that there's the law of conservation of mass, and it says that matter cannot be created or destroyed. So where does this mass go? Okay, well, this difference is what we call the mass defect, and it's the difference between the mass of an atom and the total of its components. And where that energy goes is into the nuclear, or the mass goes is into nuclear binding energy. This is the energy required to separate all the protons and neutrons in a specific nucleus from each other. And the energy, it's the energy equivalent of the nucleus's mass defect. We talked last time, I believe, it was about Einstein's equation E equals mc squared, that says that we can convert between mass and energy. And so this mass defect, where this mass is lost to, is energy in holding the nucleus together. When we talk about nuclear binding energy, we also can talk about the binding energy per nucleon, and this is found by taking the nuclear binding energy of a nuclei divided by the total number of nucleons. And we're going to take a closer look at this using the graph in figure 2018, page 516, because this predicts the stability of the nucleus. So, figure 20, page 18, page 516. Go ahead and take a few seconds here, stop your video, and copy these notes. Okay, so this graph on page 218, on this graph we will see that the binding energy per nucleon is greatest for elements of mass number 40 to 70. And the most stable nucleus is iron 56 because it has the greatest binding energy per nucleon. So what am I talking about? Let's take a look at the graph. If we take a look at this graph, This is the binding energy per nucleon. This is the mass number down here on the x-axis. Y-axis is binding energy per nucleon. As the binding energy goes up, the nucleus becomes more stable. And so we see that the most stable nucleon here, or not nucleon, excuse me, nuclide, I should say, is Fe56, iron 56, because it is the highest on this graph. This is the most stable. As we go down here, these are less stable, these are less stable. The more energy that's holding it together, the more stable it is, okay? And what we also find is the greater the mass defect, because more mass goes into energy to hold the nucleus together. So that's what I'm talking about. And in between here, between about 40 and 70, this is where it is the highest. So these are the most stable nuclei on the graph. So a question we might ask is, which of the following nuclei is the most stable? Helium-2, or excuse me, hydrogen-2, arsenic-75, or uranium-235. So what we would do is we would look on our graph. We would find hydrogen, which would be about here, pretty low. We would find arsenic, which is right about here. That's higher, so that's our highest. And uranium-235 down here. So the arsenic-75 is our highest because it has the highest binding energy, and we also see that it's the closest to iron-56. So the closer you are to iron-56, the more stable it is. We can also be able to predict from this graph whether a nucleus will undergo fission or fusion. So both fission and fusion proceed in a direction that will produce more stable nuclei as end products. And so the general rule of thumb is if the mass number is greater than 56, the nucleus will undergo fission. And if it's less than 56, it will undergo fusion, because they're trying to get to this number of 56. They're trying to get to that most stable mass number. So we can answer a question like this. Predict which of these are candidates for fusion and which are more likely to undergo fission. Hydrogen-3, technetium-97, beryllium-7, or plutonium-239. So go ahead and take a few seconds to copy that down. Okay, to answer this question, I kind of divided it this way. I put fusion over here, fission over here, said helium-3 and beryllium-7 for fusion, technetium-97 and plutonium-39 for fission. I put 56 in the middle to remind me that that's the number they're really after. And anything less than 56, fusion. Anything greater than 56 is most likely to undergo fission. So that's how I organized my answer. All right, so that is it for notes for this section. So I want you to take a look at page 520 and answer questions 3 and 4. It's very similar to what we just did with those two previous questions. You're going to use that graph, figure 2018 on page 516 to answer these questions. Okay, so here are the answers. I'll just do this, 2, 3, and 4, and I'll talk about these. So the question is, of the following pairs of nuclides, which will be more stable? Oxygen 16 or tin 119? Let me just get my books sorted here. So again, we're going to this graph, and oxygen 16 is over here, tin 119 over here. Tin 119 is higher, so it's the most stable. So that's why it's tin 119. For B, the question is, which is more stable, magnesium 24 or carbon 12? Well, here's magnesium 24, carbon 12 is down here. Magnesium 24 has more binding energy per nucleon, so it's more stable. So magnesium 24 is the answer. For C, uranium 238 or neon 20 over here. Well, neon 20 is up above 8 here, and uranium 238 is at about 7.5. So the neon 20 is more stable. And between tin 119, right here again, and helium 4, the tin is higher in energy, so it is the more stable. So there are the answers again. And then 4 asks, which of the following nuclides, would each of the following nuclides be more likely to undergo fusion or fission? Now, I'm not even going to have to really look at the table for that, because I know that for carbon 12, its mass number is less than 56, so more likely fusion. Uranium 235 is greater than 56, so more likely fission. And neon 20, less than 56, so most likely fusion. And remember that mass number is just what follows each of these. So that 12 for carbon, 235 for uranium, and 20 for neon. Those are the mass numbers. Okay, what I want you to do now is go ahead and look at page 523, number 25, which is very similar to these. So go ahead and pause your video while you do that. And more stability questions. So here are the answers. I'll just go ahead like this. Okay, so if we look at the graph again, here's my graph. My choices are between lithium 6. So lithium 6 would be, oh, this is about 10, so here-ish. And magnesium 24 up here, so definitely the magnesium 24 because it's higher. Iron 56 or uranium 235, I don't even have to really look at this because I know that iron 56 is the most stable because we've already talked about that. And then helium 4 or uranium 235. 235 is up here, helium 4 down here at 7. So definitely the uranium 235 is more stable, the more stable nucleus. So that is it for this section, and I will be back to conclude the chapter in the last video.